the 1D heat equation. The 1D heat equation is given by a partial differential equation U sub t equals alpha U sub xx, which denotes a second partial derivative. The boundary conditions and the parameters are shown on the screen. What this represents the rod with endpoints labeled 0 and L. The initial temperature profile is a simple parabola. F of x equals x times L minus x. So if we project this onto the colored rod, we see that the blue regions are colder and the red regions are hotter, giving an immediate sense of how the temperature is distributed among the rod. Next is the separation of variables. To solve the heat equation, we apply separation of variables and assume a solution of the form U of xt is equal to a big X as a function of x, big T as a function of t, times U of xt. So we substitute this into the partial differential equation and divide by this factor, which gives us a separable variables and introduces the separation constant negative lambda. This gives us two ordinary differential equations, one for the spatial component, x, and one for the temporal component, t. So when we look at spatial eigenfunctions, now we're focusing on the spatial ODE given by big X double prime plus lambda of big X, and then all of that equal to 0. When we look at this visually with the eigenvalues, we visualize the first three eigenfunctions, showing how the sine waves change with n and how each mode satisfies the boundary conditions. So when n increases, the period of this function is going to increase. We have three maxes and mins. The temporal ODE, which is our big T situation, this describes the exponential decay of each mode over time. And so we can see that modes with smaller eigenvalues decay slower, while those with larger eigenvalues decay faster. Watching these curves evolve, we can see how the overall temperature profile smooths out as time progresses, as it approaches 0. The full solution. So combining the spatial and temporal components gives this full solution. We first display the initial profile and then watch it evolve over time. Higher modes decay faster, leaving primarily the lower modes. This creates a progressively smoother temperature profile along the rod, illustrating how eigenfunction expansion models the diffusion of heat of this rod. So now let's look at a specific example. Next, we approximate the initial profile, f of x equals x times L minus x, using the Fourier sine series. Starting with the first mode, we gradually add sine terms to build partial sums from n equals 1 to n equals 5. Each additional term makes the sum increasingly close to the original parabola. Notice how the color-coded partial sums clearly show a step-by-step construction of the function. And this is made to help you understand how the Fourier sine series reconstructs the initial condition into simpler, easier to digest parts. Anyway, I hope you liked this video. Please like and subscribe if you want more of this type of content. Sorry for the delay on this video, and let's try to get to 200 subs. Goodbye.